All right, I think we're at 50 people. It might be a good time to start. Um, so welcome everyone. Welcome to another episode of GPU Mode. This is a talk I've been personally very excited about. Like one of the sort of recurring complaints on the server has been, like what are sort of like important metrics for me to look at in profiling? How do I go about optimizing my kernels? I want to give a big thank you to Vikram for inviting like both Magnus and Jackson from the NVIDIA profiling team. So Jackson is like the main PM for this project. So basically any feature requests you want, anything you don't like, this is like the person to go complain to. We were just chatting before the recording started, but Magnus was saying he's been working on profiling tools for about 15 years. I would say like throughout this time, like not a lot of sort of like dark knowledge of profiling is like very well available online. So you basically have the guy here. But before we get started, like Magnus basically gave us a heads up as to what the format of his talk is going to be like. He has maybe about 15 minutes worth of slides. And the rest, he's just going to be going over profiling traces. And so really, you can very much view this as like you're looking over the shoulder of a senior engineer on the team and kind of like pay attention to what they pay attention to. So please be interactive, like ask as many questions as you want and chat if you'd like to raise your hand. Like Vikram and I will be sort of monitoring the chat. But please, yeah, like this is your chance to ask all the questions you need. So yeah, without further ado, I'll hand it off to Jackson.
Hey, terrific. Thank you. Yeah, so I'm Jackson Marusars. I'm the technical product manager for our CUDA developer tools, and Magnus is here as sort of the lead for Nsight Compute. I'm just going to give a really quick overview of the things my team works on to set the stage, and then Magnus is going to do a lot of the deep dive into kernel profiling. So just so that everyone kind of understands what we're talking about, these are all the developer tools coming out of the team I'm on. We have our debuggers for GPU accelerated codes, CUDA GDB from the command line, and debugging integrated into IDEs as well. We have profilers. Nsight Systems is the high-level platform profiling tool to look at CPU, GPU, memory, some networking things as well. I'll give a really quick spiel on that one, but Nsight Compute is the one we're going to spend most of the time on today. This is our low-level kernel profiler to show you exactly how that kernel is executing on the GPU hardware and how it's stepping through various assembly instructions and how that's interacting with the GPU performance. Cupd is a library we have to add profiling to your own codes, and NVTX is some annotations to get a little bit more detailed performance data if you want to annotate your code. Compute Sanitizer is an automatic correctness checker for GPU applications. This is the type of tool that's going to run automatically on your application, do a bunch of analysis, and then kick back correctness results for issues like memory leaks, threading issues, all that sort of stuff. And then obviously IDE integrations. We're seeing a lot of people moving to Visual Studio Code. We have integration into Visual Studio Code, Visual Studio obviously as well, and Nsight Eclipse Edition, but that one doesn't see as much use these days. If there's an IDE that you're using that you think is not well supported for GPU computing, please let us know because we're always looking to meet developers where they are. So really quickly, what the profiling workflow kind of looks like.
Hey, Jackson,
yep,
sorry to
sure.
interrupt you. It's like I don't think you share the slide yet, is that correct? Maybe you.
Is that right? It
Or
says
I
I'm
don't see
sharing
them
my
yet.
screen.
Just wanting
We
to
can
make sure.
see, Magnus.
Okay, all good.
Okay,
Then.
so you guys see the four quadrants here on the screen?
Yes.
Okay,
okay,
perfect.
awesome. Yeah.
All right, and then yeah, we'll double check you, Magnus, when you share just to make sure. So those are kind of the types of tools we're talking about. If you haven't seen any of these, definitely go check them out. They all have their place in the GPU development cycle, and we hope that they all can help you out. Sort of the profiling workflow we espouse at NVIDIA is starting with Nsight Systems. This is going to give you that high-level overview of your platform. When data is moving back and forth, is the CPU idle, is the GPU idle, what's going on the GPU. And then once you identify that you want to really dig into the GPU kernels that are running, that's when you'll look at Nsight Compute. You'll dive deep into those GPU kernels, find out exactly how they're running on the hardware, optimize them, and the process sort of continues. If you're doing graphics, which isn't really this audience, I don't think we have Nsight Graphics for DirectX, OpenGL, all those sort of things, Vulkan, but we're really focused on Nsight Compute and the left side today. And then just a couple of slides on Nsight Systems before we dig into Nsight Compute. This is going to be a timeline-based tool. So it's giving you, sort of a overview of all the correlated performance data as your application runs. So you can see things like all the processes and threads that were running, the states they were in. A lot of libraries have built-in tracing, so you can see the various APIs as they're called. You can see memory transfers between the CPU and the GPU. It supports multi-GPU profiling as well, but it doesn't dig deep into the specific kernels on the GPU. That's what Nsight Compute is for. However, there are some GPU metrics built into Nsight Systems. So the metrics that you'll see in Nsight Systems are, sort of device-wide. They're not specifically tagged to PCs or any PC samples or anything like that. But with these metrics, you can see things like whether your GPU is full, whether you have a good instruction issue rate, whether the tensor cores are active, some things like work occupancy, PCIe metrics, NVLink metrics, and you'll see similar metrics in Nsight Compute, plus a lot more, and the metrics in Nsight Compute are going to be correlated a lot more closely with the specific kernels you're running. So I just wanted to let everyone know that Nsight Systems is out there. You should definitely try it out, and it does have some GPU performance metrics, but they are single pass. You run the application, pretty much in close to real time and get this performance data and look at it afterwards, whereas Nsight Compute is doing something much more complicated, I guess. It's doing something much more detailed to profile the kernels, and Magnus will be telling you more about that. So that was just a really quick introduction to the tools we have. I did want to mention Nsight Systems, but now Magnus is going to spend most of the time talking about detailed kernel analysis with Nsight Compute. So go ahead and take it away, Magnus.
Awesome. Thank you, Jackson.
1 second. I have a question from Dongyu. Let me see if I can unmute him. Oh, I can't unmute directly. Okay. So,
Hello.
yeah.
Oh, awesome. So on the previous slide, on the trace itself, I was wondering if you could pop that up once more. That'd be great.
Yeah, give me just a second. Let me see, share. This one here.
No, I think the one after it, on the 6th slide.
Okay.
Awesome. So on the GPU active, you show 2 graphs. One is like colored in blue and the other is really shadowed. I was wondering what's the implication between those two.
One is colored in blue and the other is shadowed. Oh, so you mean like these, I guess, yeah, teal sort of things and the lighter numbers above them? Like, is it? That's a good question. Holly, are you here? Do you know how the pixel shading works for what these represent?
So
it's all sort of, yep, go ahead.
Right. What you're looking at right there is a summary line of all of the activity across the GPUs, and then underneath is sort of the breakdown. So you've got the GPU active sections, the sync copy engine active, all the different things are broken out here. And then these are summed. So when you flatten this, you just see the summation over what's going on.
So I guess the question is, you see there's like a teal here, and then there's like a light gray, and then a darker gray above it. I guess if we had the
oh
yeah,
I'll be honest, I don't like the dark mode on these. So when you see that going on in these, what it's actually showing is that there are points within this pixel that in fact made it up to the top of that gray line. The average is where you're seeing it highlighted to, but if you were to scroll in, somewhere in there it would actually hit that. So you're seeing the maximal at the top of the gray and the average as the colored. Sorry, I misunderstood the question.
Yeah, no worries. So it's really just a pixel, density sort of resolution.
Right. And this is just a screenshot, so you can't zoom in to see that.
It's a level of detail mechanism, because it's sometimes quite difficult to see on a zoomed out view where your peaks are. If they are very short in a temporal effect, and you zoom out far, then it's easy to miss those. And with this kind of level of detail that Holly just described, is like you get the average as color, but you get a hint of the maximum value in the zoomed area per pixel. That way you can find outliers quicker, even though you don't see them in the average data of the timeline.
Awesome. Thank you so much.
Yep, sure thing. Maybe I'll keep sharing. Yeah, go ahead.
Yeah, since we're here, like I'm just curious, sort of curious about the abbreviations. So like, what's GR, what's RX, what's TX, and what's bar one?
For send and receive, so the transmission and receive is basically RX, TX is the direction in which your traffic kind of flows. And then the bar mapping, or kind of bar one that you mentioned, is like the destination of where you write data in this case. That's a shared area where the devices can share data between different PCI devices.
And then what about GR? It's below GPU active, yeah.
Oh, this is the graphics engine.
Oh, I see, graphic rendering. I see. Okay, got it. Cool, thank you.
So I don't know exactly where the screenshot comes from, but imagine like you could see like overall GPU activity, and then you see like copies in the different rows, and then the actual kind of graphics engine enabled, and then in a different area of this, you would then see like which process was enabled or currently using that engine, and you could see if they have different processes switching between maybe a compute process and a graphics process, for example, and then you would see that context switch in the timeline.
Great. Any other questions before I pass it over? Terrific. All right. Thanks a lot. Take it away, Magnus.
Let's see. Okay, I hope you can see my slides now. And then, yeah, I start with a few slides, and then we jump directly into the tool. I start with what is Nsight Compute. And yeah, as Jackson mentioned, this is our prime CUDA workload profiling tool. So think of this already as the secondary tool. As Jackson mentioned, we see this in a workflow where you first start in Nsight Systems, high-level overview, you get system information, see even if the GPU is potentially on your critical path, or which kernel takes more time, is slower as you expected. And then you jump into Nsight Compute and directly kind of get as much information as you can for this one kernel, spend some time in Nsight Compute to optimize this kernel, and then after this, you might want to go back and see that you can go back to Nsight Systems to see like what the improved kernel performance does to your overall performance. That can shift things around, or now your memory copies don't overlap anymore with your compute, or a different kernel is now on the critical path, and then you would continue with that in Nsight Compute. But Nsight Compute, for that purpose, kind of focuses very clearly on like collecting data for very short periods of time, one kernel or a small range of kernels, and we try to get as much information as we can do, and we will see what information is available. The screenshots on the right show like roof lines. We have detailed memory charts, but this goes down to metric information on individual source lines that you have written, or the assembly lines that the GPU actually executes. So very detailed there. We do have the same kind of sampling information that we just discussed on Nsight Systems, also in Nsight Compute. You can change frequencies. Sometimes you can have higher frequencies in Nsight Compute if you have a kernel that, or if you make a large capture in Nsight Systems, you might need to reduce the sampling frequencies there. And then we have a rule system that we looked into, like guided analysis. Since there's so much information, and as the introduction mentioned, profiling is kind of a little bit of an art form, or you get better at it as you go or learn it. We have a system that kind of automatically looks at the report that we captured, the database of metrics basically, and then tries to find hints in there that you can get directly kind of feedback for, hey, this is maybe something you want to look at, and this is how much time you could achieve if you solve this problem. The jump forward, I say already, it's a little, let me see if I can move this away. Yeah, sorry, one more back. What we do basically in terms of how the tools work, it's similar to other tools that you might use on a regular basis. So it's basically a launcher. Think of it similar than kind of Valgrind or many other tools. Instead of launching your application by its own, you just launch your application through the tool. You just write basically NCU, and then whatever follows is your application and all the target arguments that your application takes. And then we intercept basically everything that your application does and in how your application interacts with the CUDA driver. So that's where we are sitting with the tool. I mentioned you don't have to modify your application at all for this to work. Since we kind of sit in between your application and the driver, we automatically know everything you do with the CUDA driver. But there are a few optional things you can do to your application. One, Jackson mentioned it briefly, is NVTX instrumentation. If you never heard of it, I have the GitHub link there. It's a library that helps annotate your own code. And then you find these annotations in our own tools. So for example, in Nsight Systems, you would see ranges on the timeline. In Nsight Compute, you can use this to filter which kernel you want to profile and say only profile a kernel that is in a specific NVTX range. The second thing to mention is if you want to have metrics on source line granularity or have the ability to map basically metrics to your own source code, then in NVCC, there's a -line table flag. If you use this, it doesn't change any kind of optimizations. You can still fully optimize your code or run with like -03. The only thing the line table flag does is that the compiler writes a mapping table from your high-level code to the low-level assembly code, and we use that mapping table then to map metrics to your high-level code. In the HPC compiler, this is already enabled by default, so there you don't have to add any specific parameter. For other languages, like if you do a lot of Python development in Numba, for example, in the JIT parameters, there's also a line table equals true flag that you can use there.
Hey, Magnus, sorry.
Yep.
Go ahead.
Yeah, so I just see like a few questions in chat that are all very interesting. So we're just gonna speed run through them. I think both Eric and Jake are saying that like it seems like there's a typo. It should be probably line info and not line.
Oh yeah, that is
table.
Correct. It's line info. Yeah, that is correct.
And then there's another question by Biao He, and I'll extend it, which is like, will interception slow down the end-to-end latency? And generally, I'd like to ask you sort of how you thought about trade-offs of like sampling-based profilers versus other approaches, and why you settled on this design.
Yeah. So there is an overhead if we in basically are between your application and your driver. Specifically for our tool that is cares primarily for the performance of executing a kernel on the GPU. The overhead of having a host interception is still a concern. I wouldn't say we still optimize this and we want to have the least amount of overhead. But imagine for your kernel execution, we can do things, and I explained that in the next slide a little bit better. We do things on the host side to this to collect the data, but we try to not influence at all the performance when the kernel runs on the GPU. So that way, there's a good balance of like the actual kind of window where we collect data is not impacted, but for deprofiling, like I show in this tool, is like your performance of the application itself, while for Nsight Systems, you want absolutely no overhead because you want basically the original behavior of the application. In Nsight Compute, since we focus on one kernel, we are saying like, okay, if the performance outside of that one kernel is impacted, that is more acceptable there than it is in Nsight Systems. I hope that explains it.
Interesting. And sort of to clarify on this, like if a program is CPU bound, then profiling will like basically the results are more likely to like cause overhead, essentially, not GPU bound.
That is correct, but I would also say if you are a CPU bound, and Nsight System shows you that already, you might not want to jump directly in Nsight Compute because then your problem is basically somewhere else already. It is really meant for you have a kernel and your problem currently is optimizing that one kernel.
Okay, we have more questions. So this is a popular one. Ji Young Lee's asking, how does the source correlation work with like other programming languages, like such as Stridum?
Yeah. It does work for other languages. I mentioned Python already. Fortran works for other languages that have custom front-end compilers. Some of them generate the necessary line table or line info information for that, and then they show up automatically in the tool. So the question is really like, is the section available, that mapping section, in the actual Kubin or not? And we work with a lot of the people that build front-end compilers for those languages to make sure there is an option for this.
Okay, I think I see the last question maybe for now, which is Aviraj Bevli is asking, and basically, if you profile multiple runs of a CUDA kernel using Nsight Compute, how does Nsight Compute report the statistics over multiple runs of a CUDA kernel? I guess, like, let me clarify this question because I was also interested in this. Like, I think Eric Schultheis was sort of speculating that like NCU runs a kernel 40 times to like basically get more reliable measurements. And typically in, like, let's say if you're profiling PyTorch code, like we're quite used to running things in for loops to like avoid noise. And I'm sort of curious if you could share more detail around what's going on there.
I think it's a good segue in the next slide too, because the 40 passes that were mentioned in the chat too is like has actually a different purpose, but I explain it in a second. I think I can move on in the slide, and then the profiling collection. So there is an issue basically that we have to solve, is that the amount of data you can observe while running the GPU basically is very limited. It's like, think of it like the amount of profiling information you can stream out without using too many of the existing resources on the GPU is limited. We share the memory bandwidth, for example, and the more we stream out for profiling information, that would also kind of have an impact on the actual execution of the kernel. So the amount of data we can stream out and the amount of extra hardware this is on the GPU to observe these metrics that we collect is limited. And therefore, you cannot collect what we call like one report or an arbitrary number of metrics in a single pass. That's why Nsight Systems, for example, has a limited amount of metrics that we are able to collect in that one pass that we have for that application. Now, people already mentioned we replay that kernel a few times, and the reason for that is not necessarily only to make them more stable. We replay them so that we can collect different data on every pass. So let's say you ask our tool to collect 100 metrics, and we find out that would take 20 passes. Then transparently under the hood, when your application launches one kernel, we do that sequence that you see at the bottom of the slide that guarantees that we can replay this kernel and get, every time we profile, consistent data. Like your kernel should run basically every time as close as possible as we can make it. And every time we run it, we then collect different profile data, and in the end, we present the concise data of all these passes. You can collect metrics on multiple passes to make them more consistent, or you can oversample basically passes. But initially, it's really for the system exists so that we can collect a lot more information and a lot more data. And if we look at kind of the states that we have to go through, is the first thing we have to do is we save off kind of the current state of the GPU. Think of it like accessible device memory is saved off in a background buffer, because if we would just run the kernel 10 times, that doesn't really kind of guarantee that every path that we would do operates on the same input data, and that can have a significant difference in execution performance. Therefore, we save off basically accessible state. We optionally lock the GPU clocks so that they don't differ between the passes. You can turn this off if you don't like that. We have options to clear the caches so that you have a consistent state at the beginning. And then we would start the data collection or configure the data collection. We launch the kernel once, we collect the data or wait for the kernel to finish, collect the data, restore the context state. That would be like, if you have written an output buffer, we would restore this to the state before the kernel, and then we loop this, and we call this one replay path. I currently, for simplicity, say in the window of observation, there's one kernel, and that is what we typically do. But there are also cases where we call that range replay, where you want to have multiple kernels in that window of observation. same pipeline that I described there, with the only difference, instead of that one box that is one kernel, you could have multiple kernels in there, and you get one result then for that whole range. That would be kind of useful if you want to have the second kernel is primed by the first kernel, and therefore you don't want to clear the caches. Then you could make a range around it and still profile the second kernel with the state of kind of the cache state that you had after executing the first kernel. Or where it's really helpful is if you have effects like where you have multiple kernels running concurrently. It's still valid to profile a kernel in isolation, and often that helps too, but like sometimes you want to really optimize two kernels running concurrently, and for that we have a range profiling. The whole process is transparent to the application that happens under the hood, and then after this whole process, the application continues basically unchanged, or for the purpose of the application, the state of the output buffers after that kernel replay is exactly the same like you would have executed a kernel only once.
Magnus,
yeah.
I have a lot of questions actually,
Yeah.
if that's okay with you. So
Yes.
let me start running through them. So the first one is like when you mentioned this like context state saving, like this again, this context is being saved on the CPU, right?
The context is saved, like we look at all allocated memory that the kernel can access, and then we make a shadow copy of that. That depends where that ends up. The saved buffer is highly dependent on where you have memory left. In best case, if the buffer is, or if that memory object is located on the GPU and there's still memories left on the GPU, we would like to make a device-device copy. That's the fastest. But if there's nothing left on the GPU, which often happens, then we would transfer that buffer back to system memory. And in absolute worst case, there's an option to even save it on disk if your system is really like at the capacity. Obviously, that comes with a huge penalty of performance. So that is basically what we do there in that context state. And in the restore, there is clever mechanisms. We don't have to restore everything every time. So basically, after the first pass, we quickly diff basically what we have saved with what happens after the kernel, and from there on, we only restore sections that of that memory, like basically blocks of memory that really have changed, so that we don't have to upload gigabytes of memory every time. If that's just your input data set that's constant anyway, then we would skip that. We also skip memory objects that are already read-only. If you use the cuMemmap APIs, you can set like flags where some memory might only be accessed by read operations. Then we don't have to restore them either. So the application itself can help itself by making it more efficient if you use some of those tricks.
Magnus, if I'm not wrong, the size of the buffer is also controllable in the command line, all right? So we can define where and how much we want to store in the GPU memory.
Yes, you can kind of force this in different locations. For that context state save, it's mostly dependent on how much memory the application has allocated at that time. But the buffers you mentioned are also controllable. For example, when we do PM sampling, like this data collection of metrics, the size of the buffer we allocate for that is also controllable by the command line. So that's correct.
So there's another question in chat by Jiyoung. I will like rephrase the question, which is that like, what is the trade-off if you just had a single replay pass? Like just say I want to
Then if you collect only one metric, and that metric happens to be a single pass metric, then we don't have to do any of this. Then it's a single pass, you collect the data, you have it. In a second, when we jump to the live demo, you will see that we have like hundreds of metrics in that report to give you that level of detail that we think is necessary sometimes to understand certain problem cases. And they can simply not be collected in one pass. It's too much information. We cannot stream out that much. And the replay allows us to basically give you an nearly infinite amount of metrics if you ask for it, but you pay for it with the number of replay passes and with the overhead of collecting it.
I see. So you're really bottlenecked by like read rates essentially from the low-level counters, and then that's why you must use multiple passes.
Yes, I mean, one could think of, it's like putting just more hardware resources on the GPU to say like, hey, then I can collect double the amount of metrics in a pass. But the problem is it's a trade-off of like how much of these resources do you put in for profiling versus, one more SM to do compute, and then you get different answers for every person. And there is a balance basically on that for how much observability do you have when you when you profile versus how many compute resources do you have on the chip. That's the limited resource, and I would say that's area and that's bandwidth of writing out the data.
All right, last question on the
Mhm.
slide. So sorry, someone else was talking.
Yeah, I just wanted to ask, like on the CPU, if you run out of performance counters, you usually can do something like multiplex, so that you still do just a single run, but it switches out the counters it looks at like in a very, very high frequency, so that you get some sort of like average, which still
Yeah.
makes sense if your run is somewhat uniform. Can you do the same thing on a GPU, or do you really have to like
In
select
theory,
the number?
in theory, that's possible for the metrics where we calculate like aggregates over the whole duration of the kernel. There, it doesn't really work this way because you have to have the static configuration, and then you collect that metric. Imagine you are interested in like number of executed instructions for the total of the kernel. If you would multiplex that, then you would lose kind of the total would not come out correct. If you do what we showed earlier in the screenshot in Nsight Systems, in theory, you could say for a while I collect the data and then I switch to a different configuration. I collect something else, and then that looks multiplexed over time. That would work. But like these aggregate metrics are the ones where this multiplexing doesn't work, and then we basically serialize the collection, and that's where those replay passes come from.
Thanks.
So I think I see two more questions. So I think we're just going to keep going with questions. So I noticed here, like you have the step, which is like clear caches, and at least like within Python or the sort of PyTorch/Trident sphere, there's like a very popular profiling function called doBench, which basically clears your L2 cache and then uses CUDA events to sort of measure. But like, I'm sort of curious here, you have caches as plural. And so like, is it like that we can't clear L1 caches, or like, should we, but we're not doing it? Sort of curious if you could comment more.
Yes, when I say caches, we really try to clear all the caches we have on the GPU. That includes L2, L1, the constant caches, everything we have, instruction cache. The reason why we think that option is good for the profiler is if every path would start at a different condition, the metrics that you would see in the report wouldn't be very consistent in itself. Let's imagine like, you would clear the cache in the first pass, but you wouldn't clear it in the second pass. Then you get a completely different hit rate at the beginning of the kernel across these passes, which would sometimes kind of cause issues. I also saw a question of like an example of like a metric that you cannot collect in one pass. Imagine you would be limited by collecting certain things. This is no longer true on our current hardware, but imagine you could only collect from a cache the hits in one pass and the misses in the other. Now it's very important that if you have this as a two-pass metric for your hit rate, that you actually observe the same thing in every pass, because otherwise you would get effects where you would say the hit rate suddenly is above 100% because the two passes were not consistent. And that's why we think like in the default case, we clear the caches. If you want to skip this, there's an option to set this. And if you do only a single pass worth of observation, if you only collect a few metrics, then you might want to skip it to get the effect of like, how was my kernel at the time in the application? How were the caches primed basically at the time? But if you do a multi pass collection, then we typically say like to get the most accurate data, this is this is helpful for the quality of the data.
Okay, we have like an interesting set of questions. Someone asked a question in Latin. Quis custodiet ispos custodes, which is basically like who profiles the profiler. And I think there's sort of like a few sort of related questions here, which is that like, how do you know for sure that like the profiler has low overhead? And how do you sort of avoid, I guess like maybe it's a more philosophical question, like Wittgenstein's ruler, which is like you're measuring you're using the table to measure the ruler as opposed to the ruler measuring the table. So curious how you think about all these things.
Yeah, again, in Nsight Compute, I would take this specifically as like, we care for not impacting the kernel execution. Obviously, if we replay your kernel 40 times, and your kernel is a minute long, suddenly it takes 40 minutes to get this report. So wall clock time is different from saying like, is the data we collected then for this report or have high quality, and is that true to the execution that you had when no tool was attached? So for us, kind of, we would look at is the data, are the metrics that we report in the tool, do they make sense? Do they fit to our understanding of the hardware? Are they fitting to expectations of, like, for example, comparing some of these with data we would see from the emulator, where we can say like, okay, this comes out correct. We verify these metrics this way and say like, hey, we make sure that what you see with this metric is basically adjusting. We don't modify your kernel code in the normal runs of these passes. So therefore, we know that we don't perturb kind of the performance of one of these passes too much. The thing that we add as overhead is outside of that one launch that is in the middle of that replay path. I hope that makes sense, and I hope that makes more sense. Yeah, if we just switch to the I see the comment is like, I wouldn't say trust in the performance counter, it's trust in that we look in the performance counters and make sure that they are correct. You know, it's like there's a lot of effort going into verifying those, working between hardware and software teams to make sure that what we show there is basically observing exactly the value that we claim we look at. And then there's a lot of dedicated tests written that these are coming out right. And yeah, micro benchmarks. The first one we look at is something super simple where you can get trust into. Yeah, you know, it's like if I do a certain operation and you see exactly what happens in the profiler and those two match up, that is a good indication of like that it does what we are interested in. And then yeah, so I think I move forward for a second. This is mostly a cheat sheet, and this is for looking up later if you see this, if you start it yourself. For preparation, we had this line info. That's the only difference that I would recommend if you compile. Then the selection of metrics that you have, you can list the sets or sections and metrics, and I explained that in the live demo what the difference between those are. It's just a convenient way to you not have to write 100 metrics on the command line every time. For that, we give you kind of sections that would say like collect everything related to like the memory hierarchy, and that's easier than you having to list like 50 metrics for memory and 50 metrics for the pipelines. And sets is even higher on tab. It's basically a hierarchy where it says like a set is a section of or a list of sections that collect the full report. And then you just run this with NCU output file. You select your set and you run it, and then you get a report, and you can open the report in the UI. So I think for that, I prefer jumping into the application also just for lookup reasons and for the link down here. Since we said we are interested in very specific kernels in your application, there is the challenge of like, how do you tell the system which kernel to profile? And we have a large list of possibilities to specify this. So in Nsight Systems, there's also a right click and you can say profile this kernel with Nsight Compute. If they are linked together, then this is done automatically for you. Or if they are not fully linked, you can get at least the command line parameters that you should use for Nsight Compute. Here are just a few examples of like, you can filter by regexes for the kernel name, by instance number, that you can say like only the second kernel or only certain kernels when they are executed the first time. You can skip, and then on the right side you see NVTX examples where you could say if there is these push pop stacks that NVTX can build up, you can say only profile something when this certain name is in the stack or on the top of the stack. That helps a lot to kind of reduce how much you profile, because if your kernel has like 1,000 kernels and you want to profile every one, that's not necessarily what's efficient, because we typically say like you want to profile one and then go back to systems and choose another one next. Okay, live demo. I start with something simple. Let me quickly switch into the tool. To gain trust in these counters, the first thing we do is we take something super simple and look at that, and then later I have some more interesting samples to look at. For the very first thing, I just want to show you how this works. This is kind of the tool. Let me close this again. It typically starts with this welcome page. You click on Start Activity to set up a profile. You point to your application. As I said, for the beginning, we do a very simple vector add because then we know all the numbers and that kind of, we can walk through the whole report and you can see that the numbers come out as expected. And then as we move forward, we make it more complex. And then down here, output a file, and then we simply go and you can set your filters. In this case, it's just a single kernel. So I click on launch, and then you will see the application runs. Normally, you will get an output. If I can pause there in the right moment here, you will see that this is the output from the profiler. We currently profile this one kernel, and you will see in the output that we do like, I think 47 passes for this right now, and that creates this report. If we would have collected multiple reports or multiple kernels, we would get multiple entries in the summary table that you see here. We only collected one in this simple example, and you see like a few metrics in here: duration, the throughput metrics of like how much percentage, the utilization of the peak percentage for all compute resources, utilization of peak percentage of all the memory throughput that is available on this card. And we see already just from these numbers is like, this is as expected memory bound and not compute bound. That's what we would expect. You see how many registers were used and the grid and the block size from the launch dimension.
Magnus, I want to ask you something.
Yeah.
I was surprised to see that you're running on a 3070. So something that wasn't super clear. I've asked the question many times. I'm curious to ask you, which is like, what have you found are like important performance considerations when people are optimizing stuff for a consumer GPU versus an enterprise one? Because like again, like those get a lot more attention. So if there's sort of been any sort of simple things you notice people should be paying more attention to.
Yeah. For this one, because I wanted to show basically how we capture it locally, I have whatever I had in my local machine here right now. The other demos we have later are other. So for the Tensor course later, we look at a GB100 Blackwell card. In terms of the considerations, I would say like in general, the tool works the same way. You see differences between those chips and between the architectures, which metrics we can collect or how many passes it takes to collect. That is also something we optimize over time. The larger chips or newer chips often allow us to collect more metrics in a less amount of passes. But the counterbalance for that is like they also have more features. So then if you want to enable everything, we have back to where we started, but that keeps the number of passes basically in balance, that we constantly work on improving observability and coverage kind of the new features. Otherwise, like differences that you see between those is frequencies, number of SMs, all the things that are captured in the report that you would see. Yeah. At the bottom of this, I want to highlight this, and we look at this in the second example a little bit more. This is what we call our rules output. There, the system already makes recommendations of saying like, hey, here I found something, and maybe there is something that you want to look at. These are links that then jump into the rest of the report to explain how we come to this conclusion and what you can do to kind of fix these. This is the high-level view of kind of saying like, what does the system detect with this kernel? What's the issue with this kernel? Is there something that we can potentially fix? And it guesses a speed up basically that would assume if you can completely solve this problem, how much faster would it be, which is a good indication of saying like, is it worth for me to spend more time or not? We have later other examples where these numbers get higher, and then we show how we solve it and compare the data. The other report pages, so I go up here quickly through, there are multiple report pages, quickly showing the session. It's simply saying like, hey, what did I launch? All the parameters, you can rerun it basically with this command back here. And as we said, like if you need any device attributes that CUDA has for your device that you collected or multiple devices that your application is using, you can look at all of them here. The device information are critical input for profiling. Often it is of interest to know your grid size in comparison to the number of SMs this machine has. That can make a difference, and therefore it's important to have this captured in here. There is a raw page that's basically just all metrics that we collected in this run. So you can just basically look at all the individual values that we have. That can be exported and later processed in a different way. We have other ways for post-processing too, but that's one way you could get to all the data we collected. There's a context page, which basically just says like, where was this launch made? If there would be NVTX instrumentation, you would see the state of NVTX at that time. That could help when you look at that report in a week again. And then you know what you actually profiled or where this was in your code. And then the other two are the main pages where we now spend a lot of time on, details page and source page. I start with the details page. The idea of the details page is it's one overview of all the data we collected, and it's ordered in what we call sections. So the green lines separate individual sections. Every section has a name on the top, a description, and a table of the most important metrics in that section. And a section covers different portions of your kernel or different portions of the hardware you executed. So for example, the first section would be what we call our speed of light section. This is giving you the high-level overview of utilization of the hardware in comparison to the peak performance this specific hardware offers. And if we look at this, we would see like the first metric is like a compute SM throughput, which would say for all bottlenecks on the compute side, what is the highest bottleneck that we could find? And this is at 12% of the peak performance. And I go into that in a little bit more detail in a second. The same for memory, for all memory bandwidth and all links between all the caches. The one that is the highest is at 93%. And for memory, we also split this out for like the different hierarchies. L1 is at 16%, L2 at 27%, DRAM is at 93%. That drives basically this percentage up here and already shows us without looking at anything else to say like, as expected, this vector at doesn't benefit from L1 and L2 caches. We look at every data element exactly once. So this is a typical example of a DRAM limited kind of case. The sections itself then have an expander where you can get more information about this. So in this case, this is a visual representation of these two first metrics where you say like, okay, this is clear that this is memory bound. But you can toggle between different views up here. And you can see it's like, we could look at this in the same way that we would say like, if you are more used to looking at this from a roofline perspective, this is the roofline for this kernel. If you are familiar with rooflines, the x-axis is the arithmetic intensity. The y-axis is the flops per second that is achieved. The diagonal line that you see in here is basically your limit in terms of memory, and the two horizontal lines, the lower one is the FP64 performance, is the ceiling, cannot go above this with FP64 instructions, and this one is the FP32 ceiling, you cannot go above this. And our kernel achieve point is over here. It's right against the memory line, which kind of fits to our understanding of like, this is a memory bound kernel. If you want to get more flops out of this kernel, you have to increase your arithmetic intensity so that this moves to the right, so that you have a headroom to grow basically upwards. So this is what this kind of chart shows, and you can kind of see this in a quick way then to say like, okay, I'm on the left of the ridge point, therefore I'm memory bound, and I'm really completely memory bound because I'm against the kind of ceiling or the roof there. I mentioned already the bottlenecks for these metrics up here. There is a bottleneck breakdown too. These tables are basically the bottlenecks that we in the tool track for on the left side compute and for the right side memory. And you see that the topmost, they are sorted by percentage of peak, basically, and these top percentages equal these numbers you see up here. So basically, these two metrics are actually a breakdown of these metrics, and you see the highest value, if that makes sense. The reason I show this is it's very useful to look at this because imagine you look at a problem where your highest percentage is at 90%, and now it's interesting to know if I solve this, what's my second highest bottleneck? Because if your second highest bottleneck is at 91% and you don't fix that in the same case, then you go from being bottlenecked at 83%, at 93% to 91%, that's not a huge win. But if you see cases like here where you would say like, hey, we are limited by accessing DRAM too often, and DRAM is basically busy all the time. That's what the DRAM cycles mean. We are active in DRAM reading stuff all the time, and this is getting to 93%. What's the next one? And the next one would be moving data out of DRAM. There we are only at 55%. And you see all the other bottlenecks that you have in there. If you don't know all the names that are in there are obviously a lot, and I cannot list them all, but you see if you hover over these, the tooltips kind of usually explain every single kind of acronym you have in there, gives you way more details on what these metrics mean. That is true for every metric in the header table, for those breakdown tables, and also for the chart that I show you in a second. So that helps a lot. And you see every section can have rules output. That is again from our expert system that can link to other sections and say like, hey, we detected something in this section. You seem to be memory bound here. You really want to look at the memory analysis. And this way you can flow through this following just the links. Some of these links are external to a profiling guide that I show you in a second too, where we have even more background information in form of a documentation that doesn't fit all within the. Okay, we follow just through here and say like the next section we might want to look at for a memory bound kernel is like the memory workload analysis. So I scroll through down here. If I would have clicked the link, it would have just like brought me down here. Memory workload analysis, if we look at this is kind of a memory chart that shows the hierarchy of this specific hardware. We see later they differ between architectures. The gray blocks basically just mean like these units were not used for this specific kernel. And you can nicely follow here that you would say like, okay, on the left side is our kernel. We made a certain amount of global memory loads and stores. You can see that we have actually double the amount of loads and stores that fits for a vector add. We load 2 vectors, we write 1. It goes through the cache. L1 cache doesn't do anything. It's at 0% hit rate. It transfers in this direction 128 megabyte, and in the other direction exactly half 64. Each of our vector in this case was scaled to be like 64 megabyte in size. And then you see L2 cache has a hit rate of 33%. That might be weird at the beginning. The reason for this hit rate is like all the stores that we do are counted as hits. All the loads are counted as misses, and therefore we end up with a 33% hit rate. And you see that the data that is loaded is, again, the 128 megabyte to the left read from device memory to the L2 cache, and the other way direction, the 64 megabyte is written to device memory. You also see these little ports here that would say, like, sometimes there is a bottleneck of, like, you cannot read and write at the same time, or there's a bandwidth limitation. Each of these arrows are shown in a heat map, and each of these ports are in a heat map, and you can basically see like the DRAM port that we have here, that's the one that's at 95%. The read and the write follow then after with like 62% and some others. So this gives you a really quick way of understanding where in my chart is actually the bottleneck and where do I have to optimize. And again, it's a super simple example. I know this is not that simple in a real world kernel, but back to that initial question of like, how do we build trust? It's good to see that these numbers come out exactly like we want to have them in a simple overview at the beginning. And also here, you can choose again, if you want more details on the top right, you can get tables below here that kind of break out this traffic exactly in which memory access you did for which cache, the hit rates for each individual one. So there's a lot more detail. But only if you find something up here, you should drill down in that level. You don't have to look at all this data. But you also see, like, I just want to show this, having this level of detail helps a lot in the cases where you hunt something down that is in a way more complex kernel that is not that simple, and you have that level of detail available in that in that report. I show you a few other samples in this, and then we jump to a more interesting example. Scheduler statistics here. This is basically a warp scheduler. Every SM on an NVIDIA GPU has 4 warp schedulers. Each warp scheduler can issue 1 instruction per cycle. And this is basically just saying, like, how many of these warp schedulers, how busy are they? How many warps are assigned to each of those warp schedulers? And there's a hardware limit. There's then a theoretical limit that is based on the occupancy of your kernel. And then at runtime, we collect like what it actually was at runtime. This is the middle part. And then you have the other 2 values. Eligible warps would mean like how many on average were able to make forward progress every cycle. because the other ones, basically the difference between active and eligible, those are all stalled warps, like warps that cannot make progress because they wait on something. And we look at the stall reasons in a second as well. But that's usually something that I look at quite often, where I would say like, hey, depending on where you have a cliff in this chart, you can potentially see different cases of performance issues. If the cliff is between active and eligible, you typically have an issue that most of your warps that are currently on the GPU, they are stalled by something, and then it would help to work on resolving those stalls. Once you have one eligible warp per warp schedule on average, then you reach basically the speed of light of what a warp schedule can execute. It can execute one instruction per cycle. So even if your eligible warps would be 1.5 or 2 per cycle, you don't get faster with this. But that's kind of another limit of saying like, hey, if you are significantly below 1, then you might want to look at either increasing your active warps or removing stalls. And you see that some of this is described again in a rules output up here and says like, hey, it seems like here we only issue an instruction every 10 cycles instead of every cycle. And obviously that's not speed of light. And then it already says like, hey, jump to the warp state statistics to know what these warps are actually stalled at. And that's just the next section. We open this one up. And here you see a breakdown of like what the stalls are. You see the one stall that dominates basically all is what's called long scoreboard. And if you hover over this, you see that this is the stall when a warp waits on input from a prior memory instruction. Sorry, so technically you make a memory load, for example. In our case, you have like a request to L1, either local, global, surface texture, whatever it is. That is tracked in these kind of dependencies between instructions, and then only once that request is served, basically, then the next instruction that is dependent on it can continue, and until that's the case, that instruction is stalled. I also want to highlight like one more thing. If you open, and I do run a little bit out of in this low resolution of, I open this up, there's a metric details window on the side that also, if you click on any instruction or in any of these tables or on any kind of these metrics that we are here, you see then the name of the actual underlying perforx name. That's the library we use to collect these metrics. And then you can also see the description, all the knowledge base entries for this metric, but you can also see for most of them, like the average, the min, and the max, which would mean in this case, this is the average, min, and max over all instances of that unit. So I clicked on a metric that is a warp scheduler unit. That's why it starts with SMSP. So this is SM, a partition. And therefore you would get now the minimum, maximum, and average for this and the sum across all of them. That can help you a lot to find load balancing issues. And if you click on a different one, that would be, let me find a memory one quickly, an L1 hit rate, then you would say like, okay, it starts with LTS, which is the L2, and you see this down here, the knowledge base entry would tell you that this is the L2 cache. So if you are unsure of what the metric means or need to know more about these, open this to the side, and as you click through, it will give you a lot of information to understand like how what these metrics mean.
So Magnus, and is that tab the source of truth relative to, for example, blogs or documentation? Kind of like what's the first place people should look at?
No, I wouldn't say blocks and everything should be consistent. So I hope there is no mismatch in information between all of these. So we have a lot of blocks for the tools. We have a lot of BDC talks for the tools. So they are hopefully consistent. It really like, it is often a, I would say, slow down if you have to switch between different things. So therefore we try to pull in as much of the knowledge that is out there into the tool. And then you can have it in there while you look at your actual data, and you see like that part, or it's not just the help on the side, it actually has real numbers and it has additional information. So that can help a lot. It just like reaches more people this way than necessarily just referring to, hey, why did you not read the whole documentation, or why do you not know every single presentation we did? It makes more sense to have this within the tool whenever you need it.
Sounds good. There's one long question in chat.
Mhm.
Maybe Magnus, I'll let you read it because like there's no way I can read this out. So maybe
Yeah. Average number of warps resident per issue cycles waiting for. Yes. For each warp state, the chart shows the average number of cycles. I see. I think I understand the question. This is about this one, the stall cycles versus the how the if we show this basically in, do you have a cycle count or do you have a stall count? Is ultimately, I think, the underlying question. Think of this here when we say like the warp state in number of cycles, a warp is in the state of being stalled by long scoreboard. While think of it like between issuing a kernel twice, issuing an instruction of the same warp, instruction 1 to instruction 2, the lifetime between that, or the cycles between that, in which state are they on average? And this one is basically saying, hey, for these amount of cycles, we are stalled by long scoreboard. For these amount, we are stalled by waits. And then for these amount, we are selected, means like you are finally the warp that makes progress. And this is always at 1. So this gives you a good kind of reference of saying like, hey, selected is at 1 because that's when you issue the next instruction, and the other ones are in relation to that. So it's basically if you sum these all up, that's the space between issuing instruction 1 and issuing instruction 2. Seems to be a little bit easier to look at this, but I know some people prefer kind of different ways to look at the data, but it's the same data just presented in a slightly different way. I hope that made sense. Otherwise, contact me afterwards when we go into it in more detail. One other thing before we jump to the other example, I want to show a few more things. Instruction statistics, I just want to mention it here. You see the histogram of all the low-level assembly instructions. Just also to say, like, if you don't know them, you can hover over them. This one would be a store to global, and this is a load to global. You see that they are 2 to 1 in number. That is good. And then the fadd for the actual addition of these two vectors is the same amount of like the stores. That all makes sense. And you see like the other instructions that are there. IMAT, usually this is for address calculation. We use integer math, so that is there. But it makes a little bit more sense once we jump into the source code, but often helps you too to compare two kernels, especially if you rewrite a kernel with a different algorithm. It might make sense to understand like your instruction mix is how we call this, is like to see like which instructions are executed if you want to understand like why certain pipelines are super busy and others are not. I jump over launch statistics. Occupancy is the normal kind of occupancy chart that you know from the Excel spreadsheet. There's a full calculator here that you can open and toy around with the values in the tool to do this right here. The one section I want to mention is the source section down here. This is kind of the entry point now to that second page of the source page, where we have two tables down here, just like the instructions that have the most executed instructions to understand like what is the most costly kind of code. And then on the left side, because we were in samples, we would say these are the instructions with the highest amount of stalls. And you hover over this and you see like all the stall reasons as expected. We have basically only long scoreboard stalls. They are 99% of the time. And this directly brings you to the line where these stalls happen. So I click on this now. It opens the source page. And I could have jumped to this also by just basically switching from the details page to the source page up here. Let me quickly, there's correlation tables down here that give you statistics or information about inline functions. I come back to a second just to have a little bit more space here. I close this for a second. What we see here on the left side is your high-level CUDA C code. That's how we wrote this. It's just a basic vector add. You see like the index calculation that so many CUDA kernels have. And then basically this is the single line that actually executes some code. On the left side and on the right side, you see the low-level instructions that is executed on the device. So this is basically our SAS assembly that executes on the NVIDIA hardware. And you see that they are correlated because we have this line info flag on. If I click on a different line over here, you see that different code is selected on the right side. I do that again. So you see it jumps, that little highlight in the back jumps around depending on like which line you select. And this helps you to kind of see like, hey, what happens for this specific line? So in this case, you could see like, hey, we read two special registers, which is basically the block dimension and or a block index X and thread index X, and then we do an IMAT, which basically does this calculation of I. That is what these lines do. A little bit more interesting, kind of this line. If we go down here, you see like the LDG, and again, if you don't know, this is a load from global. The FAD is the addition, and the store to global is this down here. The tooltips will help you through this. This is what the code, kind of the compiler, made out of this. I just want to show this to kind of give a hint of like how detailed this data is that we collect. Word of caution would be, don't jump directly into the source view and only look at those numbers. First, try to understand what the numbers tell you on the details page, and then when it hints into certain lines and you know what the problem is that you look for, then we recommend jumping into source code and looking even at assembly. Not every time that is necessary, and not every good idea to make your kernel faster requires that you know every single line in assembly. That's true for CPUs or GPUs. But to show like the level of detail that's available to you, I thought that's useful to show. I can also show a little bit. These are metrics on the side. Quickly switch and make these not percentages. You can see how many stalls are on average on these lines, and you will find that this FAD here is the one that has all the long scoreboards. And that makes sense because, you know, we have two load instructions, and we said like the addition cannot execute until the loads are done. So basically, if register 4 and register 7 don't have yet the input of the load, you cannot execute the floating point addition, and you have to wait for this. And this is what this long scoreboard basically means. You have to wait for this memory. If the dependency here is not that obvious, if you scroll to the right, you see like we have we tell you that this is a global load and it reads a certain amount. We also have the register dependencies nicely shown for you, so you can see like R4, this is this line here, is written here and read here. This is basically that dependency that kind of pulls FAD back. And then the same for R7, this is this line over here, where you have a write here and a read here, and these are close together, and then you cannot hide the latency basically for that global load. And in our case, also that global load is fairly slow because we miss in L1, we miss in L2, and then we have to fetch it from DRAM. That takes a few hundred cycles, and then that FAD is basically just waiting there, and that warp says, okay, until that's done, I report a state as being not eligible, with the reason of being not eligible as being waiting on like a memory instruction which is mapped as long scoreboard. So this is what we can see here. You also see that we track like how often is this instruction executed. So this counts in warps how often this is executed, or you could also see on average how many threads are active at the time you executed that instruction. That is very good to see areas in your code where you lose basically a lot of threads, and therefore you execute certain things with so few threads that you don't reach like peak performance because you simply don't make use of the parallelism of a warp anymore. And all these metrics are also translated on the left side. So if you don't want to look at any of this, you can technically just say like, I only want to see my source code. I go in here and you see the same metrics here. So basically for this line, it would tell you this is 3 million instructions executed. All 32 threads are always on for this line. You have 3 global memory accesses. 2 of them are loads, 1 of them is a store, and all of them are 32-bit in size. So you see all of these in here. If that memory access wouldn't be like fully coalesced, then you would also see like, hey, how many excessive sector accesses is this in L1 compared to the ideal one? There's a whole bunch of metrics up here if you want more that we collect in here. This is only kind of the tip of the iceberg of what we see here. But I thought it's useful to show where we are here. Okay, I make a quick break for questions before I jump to a completely different report that I captured beforehand already, where it's a little bit more real world application. Any questions for this or what we saw so far here? Let me quickly look at the chat as well.
So one question about the kernel you just looked at, because I think I remember it got something over 90% of RAM utilization, but looking at the assembly, it wasn't doing like any like vectorized loads, and I think each thread was just doing like one single addition, and that seems pretty good utilization for such a simple kernel. Like I'm not sure if I've actually seen that on my local GPU like this high. I think more like 80% maybe. Why is this good?
Yes, it's a good question, and it is true that for other cases you might want to have a wider load, so a 128 load, so you need less threads to fill this up. In this case, the grid size is just so large that you have so many warps in flight that all make a request to global memory, and they all miss both caches. In that case, you can basically reach the peak performance of DRAM without even doing any of those tricks, because you don't get any help from the rest of the memory subsystem. Once you actually hit more often, the latency of like an L1 hit is significantly better than reading it from device memory. Then you want to be more cautious of how many instructions do you actually execute for your memory loads versus how much data is actually transferred. In this very specific case, or very simple case, is like this basic brute force, two loads per thread and one addition already leads to kind of the peak performance of DRAM.
Okay, this actually leads nicely to my follow-up question also, because we had this in one of the previous talks about the warp stall statistics, that the default seems to be just like how often did the warp stall. But if you click on these like additional things that you can show, at least in the assembly view, there's also how often did the warp stall, and there was no other warp available that could issue an instruction, right? Like, why is it not? Why is this one the default one and not the other one?
Yes, no, it's a good question. So this is basically the difference between these two columns. And as you mentioned, the difference basically between these two are one counts all stalls and ignores the fact if at the time we get the sample, the warp scheduler at that time also issued something, while the other one only counts warps that that were on a cycle where you basically missed the issue slot. You didn't issue anything at that time. It's a good debate which one is better. So in theory, I agree with you that the second one is giving you more hints on like, these are the stalls you want to reduce to actually issue more. Because if you would not have these stalls in that cycle where the sample was made, you would have actually issued something. So if you look from that perspective, I would agree the second one seems more tempting to look at. And it's not wrong to look at this. The reason why the other one can be of interest is also the other one, you can sum up the samples, and with your sample frequency and the length of the kernel, you can basically know what the sum of all these samples are, which sometimes gives you a more easy understandable breakdown, or you can put these samples in relation to your total sample count, while this is harder in the other column. But it depends heavily on like what you currently look at or what your optimization requires. Both have their, I would say, reason for existence. Both are good for certain cases. The main benefit of the other one, and why we think it's currently the default and is helpful, is it gives that ability to predict or know already the total sample count and have a relation to how many samples is this in comparison to all samples. Because it's fairly tempting in the right one to say, oh, I have like 200 samples here, and I know what the problem is here. It's a short scoreboard, therefore I can fix this. But then you don't necessarily know how many samples your total application or your total kernel has. And then it's easy that you fall into the trap of like you optimize something that in total doesn't really make any kind of real impact. That's what the left side can help a little bit more. That's the reasoning. But as you say, like you choose this up here and just enable both, then you have it. You get the total sample count as well if you want, and a lot more metrics. You can also get all individual sample count for each of the stalls if you need the number instead of just like the stack bar graph. They are all available in both of these cases, like the not issue case as well. But it's a very good question.
Thanks.
Python source code. I see one question for Python. That is my segue to the next report before more questions come in. Even though it's good, keep them coming. I hope I can answer most of them. But for people that want to see a more complicated report, let me quickly go in here and show the source code. I make this a little bit bigger here. In this case here, you see an example. This is a number code on the left side. Line info equals true is in here. So that we have the same mapping. I can click on here and you see the source code on the right as well. This is collected. The code that we actually execute here is a simple kind of image manipulation. It does a sharpening filter. The input image is RGB 8-bit per channel each. We convert the space from RGB first to HSV, and then we do some manipulation in that space, and then we convert it back into RGB. So this is what this kernel does. And we have a profile for all of this. So we go through the same steps to show you, like, this is more code, a little bit more what you would see if you profile your own kernel. I start again on the summary page. We have a single kernel here. You see in this case already, this is more compute bound than memory bound. And we see down here, the system already kind of tells you is like, hey, there seems to be like an issue with how many floating point 64 instructions you execute, whereas 32 on a consumer card. And that ties into the first question of about, like, you know, does the tool, is that aware of on which card you profile? In this case, we would say, like, yes, we know we profile on a consumer card that has like a ratio of like 64:1 to this. And then we would say, like, hey, for this, what you do here, that might not be perfect for this specific card that you have. If you would run this kernel on a different card, like on a 100 level card, then maybe you wouldn't see that rule and you would see something different. But having that knowledge kind of gives you already a hint of saying this, and it would also say, if you could remove all floating point 64 instructions, your kernel would be faster by 82%. And there are other kind of reasons. We only show the top 3 here, and then you saw that in the details page there are a few more. These are just like the one with the highest projected speed up. And I say estimated or projected speed up is not every problem can be solved 100%. You know, it's like if we tell you remove every single stall from your application, likely not happening. But it gives you already a hint of, like, is it worth my time looking at this? Or if it says like it's only a minimal amount of improvement, then you could say, like, maybe I look at a different kernel and I don't spend more time on this kernel. So that's why we think this is useful. And if I click on this problem, it would just jump you to the details page. Again, it opens up like our speed of light here. Let me quickly go to the breakdown so that you see this here too. Right side memory is basically nearly unused. We are at 3%. We barely read anything here. But on the left side, you see like the highest one is the FP64 pipeline is at 84%. The next one is the ALU pipeline. And that one would be at 13%. So that is already an indicator of, like, if we can shift things around away from that FP64 pipeline, we would have a potential for a really nice speed up in this kernel. And the question is, like, you know, how do we move things away from this pipeline? We could either look in the direction of, like, do we have to do this in 64-bit precision? Do we even intend it to do this in that level of precision? Is it needed? Can we emulate something? Can we use other kind of tricks to kind of move certain instructions to other pipelines? And as we go through this, this time I want to show you the workload analysis, basically showing which pipelines are in existence of this. On the left side, you see like the Tensor Core pipelines, the FMA pipeline, ALU pipeline, and is the arithmetic logic unit, and then is mostly doing kind of instructions like integer mat and mul and some conversions. And then most of our math currently happens in 64-bit. For an image manipulation kernel, you would say, like, is that really necessary if our input channels are 8-bit only? And it's probably not. And it wasn't intended in this case to actually do this. So we look a little bit more, how can we find quickly where are those instructions, and what does it do if we improve this? And for that, you know, I go further through this memory. We skip this time. we can look again at the scheduler statistics, and this time you see like we already started with a way lower theoretical occupancy, because we don't run at 100% occupancy. This is why you see kind of the cliff in the first step, and then we have a second cliff down here, which is again, there are warps that are stalled. You already read here that this is again the stall reason here. This time it's short scoreboards. These are different instructions, and is usually shared memory related, or can be branches in sums that cause some of these. And then we can jump also into, I scroll over most of these, we can again go to our source code. I jump into here. It would bring us directly to a line that would say like, hey, this has a lot of these stalls. They are caused by this, but we know already that we look for double instructions. So if you know double instructions like a dmul or dmat, you could look into this code and see like, hey, here I see a few. Where is this actually happening? And then you see like, hey, this instruction somehow does some double multiplication, even though we intended to basically just divide each channel by the maximum. And the maximum is for an 8-bit channel that to 65. But as most of you like know, in Numba, it's something that a lot of people run into at the beginning. Python interprets every floating point instruction first as a double instruction, and so have we then to do that in that position. And we have to then do this all in double instructions, even though it might not have been intended. And this way we can find quickly like these outliers. You can also see we have source annotations in here. These little warning messages here. There's also a source annotation table down here or source marker table that you can open, where you can see like, hey, these are expert system rules like we saw on the details page, but this time applied to your source code. And these would say like, hey, these accesses are actually not perfect. They are not perfectly coalesced like we had in our vector add before. Since we do an image kernel and we read like a normal kind of blur, non-optimized, not separated in horizontal and vertical, we really need like a little support there, and that is not optimal done in this kernel. And therefore, all these reads have like excessive lines. So we would directly come in here and you could point to those and see like, oh, this is what the system found. But on the other hand, we know for this kernel right now, memory is not our biggest issue. So we can ignore them right now. We only focus on like getting rid of those 64-bit math instructions because we didn't intend them to do so. So I changed the code, profiled again, and I show this primarily now to show you the workflow in the tool. It is very common in profiling that you make a profile, you look through it for a while, you build a model of like what you want to change, and then you go back to your editor, modify your kernel code, compile it again, and then you make a new profile. And then the big question is like, did you achieve what you wanted? And to show this workflow in the tool, because this is what we do on a daily basis on our end too, I wanted to show you this with this simple example. We know now we want to make these floating point 32 instructions, and I made a new report. So basically, I go back and I open this report. And now the question is like, okay, how do I compare this? Do I really sit here and kind of constantly jump between those two tabs and see like, yes, I can see my time here. If you see duration is significantly better in that second version than in the first one. But it is fairly difficult to do this for all metrics and see like, hey, did that change maybe have a negative impact on something? For that in the tool, we have a diffing in the tool so that you can actually see those differences directly. And this is with compare up here. I'm currently in the first kernel that we looked at, like the one that still has 64-bit instructions. You add this as a baseline, and then you see now this is kind of a baseline. And now if you go to a different report, you immediately see like that all of them are shown as the real value of that new kernel, but also percentages to the baseline. And therefore, we can basically see up here, if you remember, duration was predicted in that first kernel to be 83% faster if we would remove the 64-bit instructions. And here we have like an 81% speed up for this. And therefore, you see like, okay, this is going in the direction of the change that we wanted to make. But you also see with these background bars, like the purple is basically a high negative change to the metric, and the other color, and you can change the color if this is not the color choice you want in the options. And the other color is kind of a high positive change. And you would see, like, if we reduce the runtime by 81%, our utilization or closer to peak performance goes up significantly. We are still far from having kind of 100% there, but you see that our utilization of memory simply went up. We didn't change anything with memory, but since our runtime reduces, the utilization goes up. And you can see the other one too is actually, the other one went down because this is utilization of peak. This is not kind of efficiency. So therefore, even if you make a good change, this can go down. And now we can look through basically where did it have positive effects. So let me quickly look at the compute workload. You could see the green one, our baseline had these FP64. You see we didn't really fix all of them yet. But in the blue one, our most busy unit is now the ALU unit and no longer the FP64 unit. And we can do the same thing for all the other metrics, including the source page itself. I don't, before I jump to the source page, you can see, like, down here, what actually happened is we have the same hardware limit, the same theoretical limit. We launched it with the same occupancy. But now, because we don't wait for those FP64 instructions all the time, our eligible warp scan went actually up quite a bit. So we are way closer to 1, and we can actually issue now not 1, but like 0.7 instructions per cycle, while previously we only issued 0.13. So this is kind of the effect of moving these instructions away from this fairly slow FP64 pipeline on this hardware. But I wanted to also show the source page. Already left this in that state. You see on the source page too, basically the only change we made is this number float 32 around all the constants, and then we ended up with this. Also for the comparison, you can go up here and just say, like, oh, I want source comparison between the baseline and my current. Then you now get this kind of diff in here, and you would see, like, in red all the numbers that have changed. But the nice thing with that diff, this is not your diff that you see in your editor, or when you use your code editing or repository to say, like, hey, what did I made a change in there? This has still all these metric attached. So you can see kind of the differences in what did that do for this one instructions that we did in here. You see, like, on the left side, we had a lot of samples on this on this one line that did, like, all the double divisions. On the right side, this is significantly less. And you can also see, like, the stalls are completely different. The mixture of the stalls can be completely different, and therefore the next problem you look at can be quite different. So those are just, like, workflow ways of telling you is, like, the tool kind of is prepared for this workflow of you make a report in the morning, you made a change, you make a new report, and you want to compare the two. You can have multiple baselines too if you want to compare different variants of your algorithm, different grid sizes. That is there. We also have some limited way of running profiles automatically and changing some parameters. So we call them profile series, so that you would say, in the limited ways the tool can change your kernel execution, we could say, like, hey, make a whole analysis and profile this kernel under different conditions a few times, and then you can compare all of them and see which one is the best. That is called profile series, is built in the tool as well. Because this is kind of the workflow that we see all the time on our end. You make a change, you understand what this change does to the target metric that you wanted to optimize, and then you also look, like, what other side effects did that have to the rest of the metrics that you see in this report. I hope that makes sense. If you want to get rid of that baseline, you just go back here, clear baseline, and then you basically see the report as before. You can save the baselines, you can give them custom colors, name them, you can share them with your colleagues if that's necessary, so that other people can say the same thing. Sometimes you work in a team, and that's pretty good. Some customers use this as saying, like, this is the baseline of we don't want to get lower than this, and if you make a change to the kernel and add a new feature to it, you cannot get lower than this performance, and they use this as regression testing sometimes. all of these options are there if you want to use them. Okay, I wanted to show one more example. I switched to the last, and then we have hopefully a lot more time for questions at the end. This last one is a kernel that does an tensor core operation. It's very simple. I only used one block, basically, and 8 warps to do this. For simplicity, let me quickly switch back because it's always tricky to kind of get everyone on the same page. We do a tensor core operation on a GB100. We have, I don't do the addition for simplicity. We just do A times B and write it to C, the sizes you see here. Basically 16 kilobyte of the 2 input matrices and 32 as the output. We all do this in FP64, so half precision. We launch one block with 8 warps, 250 threads, and then the sequence is basically, and I want to show you how these things show up in the tool, so when you see them in your kernel, that you can see where you expect that data. We use the TMA engine to actually copy the data from A and B, from global to shared. The TMA engine is a efficient way of kind of copy between those 2 memory spaces using like a copy engine to copy this, and it can happen async to your actual work in the kernel. So we move these into shared memory. Then we execute tensor operations. We execute 4 in here. They all have a size of 128, 128, 16, and this together then builds what we need for this matrix multiplication up here. So we execute 4 MMA instructions. They read their inputs from shared memory, and we allocate and accumulate all of this in the tensor memory that this hardware has. And then in the end, we need to read the result somehow out of this TMEM. We just do this with reads directly to register file, and then we write this traditionally just from register file back to global memory. And now we want to see, like, can we find all of these things in our actual report, and how does this show up? So I jump back to this. We jump directly to the details page. Speed of light. If we only do one instruction, we don't read performance, obviously, but I wanted to show you here the tensor core roof line. There's a specific roof line that tells you that can be quite helpful is of the many different operations that a GPU like this can do with all the different combinations of source and inputs, which one did you actually use in this kernel, and how much of the peak performance did you use? No surprise here that for executing one, we basically don't stress the GPU at all, but that helps us to make easier math. If we look at the memory chart in a second, just imagine if you would scale this up and use way more warps or make this grid a lot larger, then you would also kind of get closer to this peak performance. But while I show this, it's super helpful because we often get the question of like, hey, can we know which tensor cores, which formats we are using, how close are we to peak? This is basically where you find this in the tool and gives you a hint. Some of these instructions I want to show, like, since this is the same, this is a special kind of ultra tensor core, kind of a fast way of doing this, and then they show up down here again because it's the same input and outputs. That's why you see 2 points up here in the roofline chart, and you see we are far away from any ceiling. So with this single or kind of 4 operations that we do in this simple toy kernel is not getting close, but I hope it helps if we then look in our memory workload analysis. So this chart already a little bit bigger because we are now on a more advanced hardware. The other ones that I show you were a little bit smaller. But here we see we have 2 instructions to the TMA unit. So this is basically what we said, like we copy the input matrices A and B from device memory up here into shared memory. And we said both of these matrices are 32-bit in size, are 16 kilobyte in size. So you see basically here, if you hover over this one, this says like, this is the traffic from L2 cache to shared memory executed to TMA unit. So these 32 is matrix A and matrix B executed through that async copy operation that the TMA unit can offer you. So basically what this does is you prepare a descriptor. It says like, here is my memory, and I want this loaded in shared. You execute this. You can actually then execute async for that copy, completely different instructions. And then later you can ask like, hey, is this done? and then your data ends up in shared memory. Then we said we wanted to see 4 instructions of tensor operations. This is this down here, and you see it reads the data from shared memory that we put in here. It makes these requests, writes the data then out in tensor memory. So in the end, our output of C ends up here, and you see like this is 4 instructions. The data flow kind of goes in here. It iterates between tensor memory and the inputs, and our output metric C is basically now residing in this tensor memory. And then we said what the kernel does at the end is once those 4 operations are done, we read the tensor memory directly with 4 of these warps. That is arbitrary, but like I show you the code later so that you can see why this is 256. We read basically this tensor memory back to the register file of the kernel, and then up here we do simple stores that write this into shared memory, and you see the 32 kilobyte flow back into L2. You don't see this in DRAM. This is so small that L2 basically never has to flush anything. That cache basically only evicts something if you have a pressure of evicting a cache line. So basically that's why this 32 ends here, and we don't see the write to DRAM. Once you would have a larger kernel or there's a need because there's more lookups in L2, then you would actually see that the lines get evicted and you would get the 32 kilobyte also in device memory. But I hope that makes already sense that you see like even for something more complicated than this, you can see kind of the data flow in here. The shared memory access, the kernel uses some barriers to kind of wait for this TMA instruction and wait for the tensor core to finish. These are the few shared instructions that we actually do because we have that barrier located in shared memory. Yeah, that is what we see in the memory chart. I quickly show again the source view for here. Again, the same thing that we have source correlation in here. I scroll down a little bit to where we do the actual instruction. This is like the TMA code. You would see like we make this copy instruction that copies something basically from global to shared. And if we just click on this, you would see like, yeah, this highlights this code. It's executed exactly once. You see like one thread executes the whole memory copy. And then this is basically executed in the background while we do other work. In this case, we also execute the second one. If I click on this, you see they are lightly inlined. If you see like those 2 instructions, if I toggle between them, basically the compiler kind of interleaves them nicely so that this has the most efficient execution pattern. And then, yeah, we've set up a barrier so that we can wait on this. This is the way we execute this. Maybe one more thing to show here before we open it up for questions would be in the end down here, we do, yeah, this is where we copy then the data back to actual memory. And one interesting case that I wanted to mention here, this loop is executed by 4 of the 8 warps we have in here. In this loop, n tile size is 128. So basically, this 4 instruction or 4 loop is executed. We increment by 2, so it's executed 64 times. The compiler actually unrolled this loop, and you can see this in this mapping. So that's why I wanted to highlight this. If you look how many store instructions we have, like the STG, you would expect 2 from this code and then a loop around it. But you actually see 16 if you count them over here because the compiler chose to kind of unroll this 8 times. And then we see like 8 store instructions for each of these. And if you again go to the other one, you will see 8 here. Same is true for the instruction that loads tensor memory to register file. We would see 8 of those. You can see this back here as well because the sum nicely sums this up, that it says like this is a request to tmem load and it's 8 of them. This is a request to store something in global memory and it's 8 of them. And then that's how you can come up with like understanding sometimes like what happens or why this is like this. Often also requires that you kind of see like what the compiler actually did with this. But it's visible to this here, and it helps kind of to understand like sometimes low-level metrics if you know exactly what was executed. Okay, I stop here for more questions, and I think the rest of the time we spend for questions. And feel free to ask any of the tools questions, or for, I think Holly is still here for Nsight Systems, and I think Jackson is still here too for the overall tools that he described at the beginning.
Cool. Thank you, Magnus. This is awesome. Yeah, folks. So if you have any questions, like feel free to just like raise your hand or either post them in chat. We can just do voice questions now. I guess I just see like already one question. I think this might not be super directed to you, Magnus, but it's like around whether consumer Blackwell has tensor memory or not.
No, that is that is not there on the consumer Blackwells. And you will see then, that's the other nice thing, is like if you would have run this kernel on a different or your similar kernel, the memory chart adjusts basically to exactly the units that this card has that you have. And the memory chart therefore looks completely different. If I go back here, this one is a very simplified one. It's not because we didn't collect the same amount of data. It's really like this is a different hardware. This was consumer level or like an A10. And this one was like a Blackwell card, and you see that there's a lot more features in here and a lot more coverage. Goes back to that earlier thing of like, yes, this also requires to collect more metrics to get this chart fully filled out. But it's roughly the same amount of passes because we are more clever in merging passes together, and we work every architecture to reduce the number of passes, and then we add a few features to it, and it's back to 40. Yeah, that is how this works for us.
So another question, this might be on the shallow end, so please forgive me, which is like basically when you look at a picture, like for example, like let's say in the PyTorch profiler, I have like certain visual cues that I know things are bad. If I see like many small little blocks, I'm like, no, there's not fusions. If I see like lots of empty space, I'm like, oh, like there's like a lot of waiting happening. And so I'm sort of curious, like when you look at a picture like this, like what are sort of the main visual patterns you're looking for? Like, do you want everything to be orange or not? Like, is there like any sort of common shapes that you found helpful?
Yeah, it is. It's a good question. I'm not sure if I have like a perfect answer for like how this really works. It is a lot of a lot of experience, I would say, is mixed in there for sure. When you have, if I look at the memory card like it is shared right now in there, you would have the kind of I first look at, like I said, like the highlights of like which units are on, which ones have the highest peak percentage. And then in terms of optimizations, there is always the question of like, can I shift things around to either reduce the bottlenecks or maybe use units that I don't use yet. There are so many ways, for example, to copy data from device memory to shared. You can do this traditionally with just like a global load and then a shared store. There is optimized instructions that do that with LDG STS that avoid kind of the register pressure there. And then we have TMA now that does this. So yeah, those are things that you would say like, if you have options to do certain things, then you can find ways of saying like which one is more efficient or which one applies more to my kernel. And it's helpful to see this in a chart because then you know exactly like, hey, which parts are hot basically and which ones are currently underutilized. And then you can shift things around. The optimizations are often kind of a problem of utilizing as many of the units that you have. It's like the same thing for like the pipelines. If your instruction mix only uses one instruction pipeline, it's very hard to be super efficient and make use of everything the GPU has available. While if you are able to express this slightly different and your instruction mix becomes more friendly in terms of which units or which pipelines can execute the code, then you get a balanced execution and you might use more execution pipelines that hides latencies better. It's like it's always an act of like saying like, hey, what do I use and what do I not use yet, and can I shift certain workloads between those?
Yeah, I like this. So basically, like it sounds like your eyeballs immediately go to the gray boxes. You're like, what's going on here? Like why? And then this is like this can lead to an informative insight. Okay, so I do want to read the question.
Sorry, to add my 2 cents to answering your original question, Mark, about like initial things you look for. And I was talking about this in the chat a little bit about like doing some napkin math and then kind of coming and confirming it here. That like if I have a particular algorithm that I know it's reading n bytes and writing n bytes, and like that's all it should be doing, then I come and look at this and confirm that like oftentimes it's just like, am I moving as much data as I'm expecting? And oftentimes I'm not, because I'm not doing vector loads appropriately, or I'm not caching appropriately, or something like that. That's oftentimes like 90% of times when I use this tool, it's just like identifying pretty simple things like that, of just like not moving, usually moving too much data or not hitting in cache as much as I would expect to, just kind of like building an intuition ahead of time and then coming and double checking and is like, okay, is my intuition actually right? And if not, like that usually means there's something wrong, and go look for why.
Yeah, I think that's a really important case, Jake, for saying if the more of an expectation you have from writing your kernel, the easier it is to kind of confirm that you reach exactly this. You know, it's like you know how much memory you usually access for your algorithm, and from an algorithmic perspective, how much memory you expect to transfer from device memory, for example. And then you look at the tool, and sometimes you get surprised. It's like, hey, this is actually 10 times more than I wanted, and somehow this is not what I expected. Or because of the access pattern, you know, you get a lot more traffic between L1 and L2, even though you access only a small amount of data in DRAM, but the way you access it kind of makes some of these things explode. And I think this is the things you see nicely with this tool. You have that expectation, or your understanding from a programmer perspective. I develop a solution for this problem, and this problem requires a certain amount of instructions or a certain amount of operations, and then you can confirm in the tool, am I completely off from this expectation? Is it matching to what I want? Or as we said, like, do I even use the right instructions? Sometimes even that can be a very basic thing of saying, like, am I using the tensor cores that I wanted to use, or did I do something completely different? It's nice to confirm here to say, like, yes, what I'm doing kind of gives me exactly what I intended to do, but that expectation helps a lot. Mm-hmm.
Yeah, it's interesting. I think both of y'all's feedback was really around like just identifying like the dumb mistakes and not necessarily sort of like looking at the specific data flow, kind of like the logistics problem necessarily. I guess like maybe that's like more true for like kernels that are like better studied. So I do want to make sure like other people get a chance to ask questions, because I think I can keep yapping about this. But I think this is a question to Holly from Arun, which is like any advice on how much time deploying takes from running Nsight Compute for the first time, and sometimes after reboot on an instance, it's really long on some machines. So like any advice on startup times for Nsight?
That's actually still an Nsight Compute question.
Oh, I see.
Is that for compute? Yeah, thanks, Holly. No problem. Any advice to minimize how much time deploying takes when running Nsight Compute for the first time after a reboot? Yeah. Like I'm not 100% sure if I have a perfect answer for this. My question would be, so when you run Nsight Compute on your target application, there is some setup that we do at the very beginning, but this is for every run you do. So I'm not aware that like the cold kind of after reboot setups could be significantly different than runs that happen afterwards. That should not necessarily be the case. And if you see cases like that, let us know, so that we can look into that a little bit more. The overhead that we described, kind of when you run Nsight Compute on your application, the things I typically see is like filter kernels. If you have a report with like hundreds of kernels in there, then we would say already is like, hey, first look at this with Nsight Systems and not collect hundreds of kernels in Nsight Compute. Sometimes if you run something overnight, it's supported, you can do it, but it goes a little bit outside of like what we think we do internally, like a lot with this tool. We typically say like we target one kernel, we look at that one kernel, and then we move on to the next one, but we stay with that one kernel for a while. If you have a report with hundreds of kernels, if you make a change to one of them, that can influence all others. So it's like it's hard to kind of really have this. I can profile everything at the same time.
Hey Magnus, quickly on that one. I think this person asked an earlier question as well. It's more about deploying remote files.
I see.
When like a lot of overhead deploying remote files for remote profiling. Any tips there?
Yeah. If you do remote profiling, we have to copy over the files for the first time. It shouldn't be. We currently deploy them in the temp directory, and that could be the reason why you have to redeploy it on reboot. You can choose a different directory if you have space somewhere else that's not necessarily deleted in between reboots, or then you could have this stable. The other thing that we did is there is finally an libSSH version available that has way better upload speeds, that has in our tool also like a 10x or even higher improvement in that deployment. So hopefully with more recent versions, you see that like that time that used to be super slow and you see every single file being copied should become significantly faster with newer versions, simply because we had a better way of kind of implementing that upload. Yeah, thanks, Jackson, for clarifying this. I think we had one hand up.
Yeah, so Dong, please, you should just say your question.
Also, I had a more general question about the roofline having different plots for each cache level. Would they, for example, be used to measure the improvement in cache data reuse, or are there any example cases in which you'd use that in a performance sense?
Yeah, for the analysis for the roofline, yes. All three of the caches have different. Let's go back to this one. They have different bandwidth available, those caches, and therefore the memory side of that chart looks different. I didn't collect the right one that I wanted to show you. But in general, if we look at this, it's like you can see the achieve points. So if we have that roof line that has like the L1, L2, and DRAM line there, you can sometimes see, because you get also 3 achieve points, and they are usually on a horizontal line. And depending on where these lines lie in comparison to the ceiling, you can see on which of the caches you might be limited. And that can give you a hint of like you have to work on something that reduces the the efficiency in L1 or the efficiency in L2, because one of them can be your bottleneck, but not all 3 at the same time. So that's why in this chart, where you have like the hierarchical roof line with multiple kind of ceilings for memory, the thing I look at there is basically the achieve points, which ones are limited in hitting their ceiling, which ones are not, and how are they distributed on that horizontal line. That can give you a lot of hints of like where in the memory subsystem is your actual kind of bottleneck.
I see. In that context, I guess like L1 cache roofline would also include all the data transaction that also comes from the lower level memories as well. They're all included, for example, on an L1 roofline, not just data that's directly sourced from an L1 cache.
I'm not sure. Are you referring to shared memory in this case, or what do you mean with like lower level in that case?
For example, when you plot an L1 cache roofline, would they also include all the data transfer that comes from the lower level of memories? For example, global loads also bypasses L1 through the SM registers.
I see. Yes, it does include the other one. So basically everything that actually flows through L1 would be included in there. So that includes kind of all the traffic, you mean? So that is kind of in that sense, like L1 includes everything that kind of the kernel sends through L1, if that makes sense.
Awesome. Thank you.
So I see another question from Eric. Go ahead.
Yeah, I also wanted to basically kind of like re-ask or reformulate a question that was in the chat earlier. which I think goes back to the fact that if you look at the CUDA programming guide, it tells you have so many integer cores and so many floating point cores. But then if you look in the profiler, you actually see that this isn't really what's going on. And I'm not sure if that's so much as a question and more an opportunity to maybe for you to explain in this context also a little bit, like something that's surprising to someone using this tool for the first time, maybe that integer multiplication actually ends up in the FMA pipeline and floating point comparisons, maybe they're not actually a floating point.
Yeah. It's a good question, and is something we kind of deal with quite often. I would say it this way: your model of the GPU kind of there are different levels of model. You know, it's like there's nothing wrong with looking at it from a CUDA core's perspective. That model is very useful for the discussion of an SM in the white papers, and that's why this is used there. The model that we have in the tool is indeed slightly different because when you collect the hardware metrics, they come from the hardware as it's implemented, and therefore your model might have to adjust a little bit. That doesn't invalidate the other model. It's different levels of abstraction is the way I look at this. And yes, that can be kind of confusing if you have one model in mind and it doesn't fit kind of the tool that you currently look at. But it doesn't necessarily conflict in any way. So if you look at the white paper model, the amount of cores we have, they do correlate to kind of the throughput of these pipelines that we show in the tool. And they are kind of the models kind of overlap and make sense, but the way we describe them or kind of are useful to look at the metrics we can collect in hardware. In some areas, we describe the model in a slightly different level of abstraction. I think this is the way I look at this. It's not that we tell you something wrong in one. It's really like a different kind of abstraction layer that makes it easier to describe certain things on that level. And metrics tend to require a model that is a little bit closer to the hardware because the events or the metrics that we collect are simply collected at hardware at runtime. So there, it's harder to sometimes make these higher level abstractions that that are so convenient kind of to look at, but then the metrics wouldn't fit to that as well as it would do to a more fine granular level, abstraction level. I had like one while we, and I'm happy to answer more questions. I just want to quickly switch back to one more slide because I know a lot of you are experts in and have a million ideas on like what can I do with all these metrics and maybe do visualizations and things that we don't have in the tool yet. We have a full Python report interface. So basically our report file format is fully public. That is documented. It's based on Google protocol buffers. But even more convenient, we ship a whole Python module that allows you to simply kind of open a report, iterate over all the results in it, iterate over the metrics that are in there, and you can just like go from there and build your own post-processing step. I have the link in here, and there's some Jupyter notebooks that help you kind of getting set up with it. If you are interested in that and the tool itself is not giving you everything you need yet, and you have ideas of do other post-processing, give that a try. That helps a lot of people to kind of get access to this. And then if you come up with something cool, let us know too. Then maybe we can add this to the tool in a future version. And if it's very helpful, then everyone benefits from it. But that's one of the things that I wanted to mention. Is very popular, and a lot of people kind of, especially when they have ideas of like how to post-process more of these metrics or see more in the tool that helps. I would also mention all sections, all rules that run, they are also editable and data-driven. So if you want to see all the sections, the metrics we collect in the sections, those are text files on disk that you can look at and modify. And then your tool looks a little different if you modify this. The rules also are simple Python rules on top of the database. So you can see like how we estimate the speed up, when that rule fires or when it doesn't fire, or you can add your whole new set of rules if you want to the tool. Hopefully the ones we ship with are useful, and that is kind of the intention, that we ship and have all the important ones in there. but more people have more clever ideas, and that's why we think this can be useful if the tool is extensible and can be adjusted to your specific use case. So that is one thing, and then the last slide that I have is just additional resources apart from the server that we have for this discussion. You can download it if you installed it through the CUDA toolkit. It's already there. Documentation, we have a forum if you want to ask questions there. Lots of training videos, and if you happen to be around, look at our next set of training videos at GDC, or if you are there in person, come by, and a lot of us are there, then we can even talk in person. That's all I had, but any more questions?
On the topic that you just mentioned, is there a convenient way to just export a single of these graphs from NCU into a picture? Because that would be often really, really useful to just share when you talk with people about a kernel that you're working on.
Yeah, we have an export kind of there that can export the whole report with everything expanded as an image if that's needed. There's not a good export in PostScript to use directly in a paper, for example. That's something that would be nice, but we don't have yet. But for images and for exporting data, that's all there. So for example, you can also export the source view directly in CSV file format from what you see on the screen.
Yeah, I guess I was mostly thinking about putting the memory view on the slide or something like this. I think that's one of the main use cases.
Currently that's a screenshot then, and that works. But I agree, and we find ourselves in that same situation. We often make this now on internal presentations too. You have set a few baselines, give them good names, make a screenshot of it, and you have nice charts in the tool already that would be useful for presentations as well. Let us know if you hit any boundaries there, or you have good ideas what we should do different there to make that workflow even easier. It is something that we find ourselves use like this also quite a bit.
Yeah, I mean, I just want to plus one. I just want to plus one this and say, like, if anyone is like working on like better profiling tooling or like different visualizations, we'd like really, really love to hear from you on the server. Like, I think like within PyTorch, like we had certain like tools like HTA that just gave people like reports of like, here's what's happening with your distributed job, and we'll just give you, for example, a number for like, here's like your comms bottleneck, here's your compute bottleneck, and people really enjoy these like smaller reports. So would be very, very interested to hear more from you if you're working at the intersection of the space. All right. Well,
if there's no more concrete question to the profiling tool, the last thing I want to maybe ask goes a bit broader in scope, which is that like when I'm optimizing CPU code, one option is to do profiling guided optimization, right? Like have the compiler actually use the information about what are hot code paths, or I guess in the GPU, like figuring out which instructions stalled and maybe influence the code gen automatically. Is there something like this, or is that something that is maybe planned? If you can say.
Yes, it's there is something like this. It depends a lot on like what your pipeline is, what language you write in. So I'm not saying like, hey, every high level language offers this way, but like for some there is ways of using profile guided analysis and feed something back into the compiler, so that that you can have benefits there. But yeah, it's still also an active field, I think, to improve even further.
But wouldn't this, for basically all languages, go to the PTX layer anyway? So at least at the translation from PTX to SAS, you could have this profile guided feedback.
Yes, agreed. Yeah, that would be an option. Yeah. In limited ways, I think we have some of it, but I think there's maybe more ideas to follow there.
Thanks. I mean, anyway, it's not really the topic of this talk. It's just kind of like the next step that maybe.
Yeah, I mean, at least I would say, like, if I bring it back to the tools, is like with the source view and the correlation there, it becomes a lot more possible to understand like where maybe the choices are not optimal. And sometimes you can then make some of the changes in your own code, but it would be more convenient if this is kind of done perfectly for you. But if you see cases where you think we could improve, that is also feedback that would be of interest, because that is a constant effort to generate the most optimal code we can from any input.
Yeah, I think I've seen cases where manually just moving some loads earlier on reduced warp stalls, and the compiler wanted to reduce register pressure and move the loads later, which is also sensible if you don't have, like, I wouldn't have known without looking at the profiler whether which of the options would be better. And I guess the compiler is in the same situation, right? So
yeah. There is, so we have in recent versions, you saw the little triangles on the source page, and we said like, oh, this instruction has less, less optimal memory access patterns. We have other what we call annotations from the compiler that we can show there. For example, for local instructions, we now can separate, is this local instruction added from your user code, or was it added by the compiler for register spilling, because you told the compiler, you had a certain register pressure, and therefore it used local memory as like the backing store for spilling some registers. Before, it was very hard to kind of get a good feeling for, if you use local memory in your kernel, how much of this traffic is because of spilling and how much of this traffic is because I actually use local memory. And with these annotations, we can now separate this. And I think your question goes in the same direction of like, the compiler makes so many choices and has so many knowledge of like why he does, like why the compiler chooses certain optimizations or maybe fails to apply a certain optimization, that we also see as a high value of providing that information to a developer that currently tries to optimize their code. And you will see like we extend these annotations over time. Every new version will have a few more. And I hope that can help then also to kind of close that gap of what do I have to do in my code to maybe get that optimization that I read about in a blog post, but it doesn't apply in my case. And somewhere in the compiler that's known, but it's sometimes trial and error to find out. And I think with this pipeline that we have built there, with the annotations for kind of the compiler tells us about spilling or not, or about loop unrolling, why it shows as 8 and not 4 and not 16. Those are things that we hope we can solve there, so that there's more understanding of like when this happens or why it happens. I think it's a very good question and a good area where we can do even more than we do today.
That sounds very cool. Thanks.
Mm-hmm.
All right, I think this might be like a good time to call this. Thanks again, folks. Magnus, Jackson, Vikram, Holly, Jake, like thank you so much from all the folks on NVIDIA for presenting this. The lecture will be on YouTube like very shortly. Just give me like a day or two to edit it. And then tomorrow we have another lecture. It's going to be by Pranjal SSH, who's going to be talking about how he outperformed Kublas on an H100. So it's going to be very similar to Eric's talk from last week. Thank you, folks, and we'll see everyone soon. Thank you.
Thank
you,
awesome.
everyone.
Thank you.
Thanks.
I'm going to stop the recording.